Hello, this is Jack Jackson. This video, we're going to talk about a pretty fundamental thing, and that is whether we want to use an SAS postulate or reflection postulate. And one of these ultimately will become a postulate, and the other one will become a theorem. So we have already assumed an SAS postulate. So let's start with that perspective first. We claim that translations, rotations, and reflections are isometries, and we've already proved that if it's an isometry, it's got to be a congruence mapping. So we must prove that translations, rotations, and reflections are each isometries. And we did this in earlier videos, or maybe in one case left it for an exercise, that translations and rotations are each isometries. And now we're going to do the same thing for reflections. And recall that we're assuming that we already know all the earlier postulates and previously proved propositions, so they can be used as reasons in the following proof. So our theorem is a reflection is an isometry and then thus maps a preimage to a congruent image set. All right, so here we go. We assume that the postulates and proposition Euclidean geometry proved thus far are true, including the SAS triangle congruence postulate. So I want to make the point that this is directly related to and dependent on the SAS postulate. So we're given triangle ABC and a mirror line M. Let A prime, B prime, and C prime be the images of A, B, and C respectively under a reflection about M. By definition of reflection, the line segments going from the preimage point to the image point are perpendicularly bisected by the mirror line M. Let X be the intersection of the line segment with endpoints A and A prime, the intersection of that line segment with the mirror line M, and let Y be the intersection of the line segment B prime with M. So notice that both A prime, that line segment, and the line segment B prime are perpendicular to M and are thus parallel to each other. Now there's 5 cases we want to look at. The first case I don't have illustrated here, but it's the easiest one. Suppose A and B are both on M. So if that's the case, each point of that line segment AB is fixed. So not only is the distance AB equal AB, but also the line segments are actually equal. Okay, and so certainly that proves, this should say, not only is A prime that, but A and B are so maybe I should be explicit. So A prime equals A, B prime equals B, and the distances are the same, and those line segments are the same. So that's sort of the super easy case. So let's assume that exactly one of A or B is on M. So without loss of generality, let's say it's B. Okay, do I have that? I don't have that one pictured. Maybe I should put in a picture of that one. Okay, so here's our illustration. We've got B is on the mirror line M here, and A is not. So then you reflect this over. A prime will be directly on the opposite side here, so that the line segment A prime is perpendicularly bisected by line M. Let X be that point of intersection there. So if you look at what we have here, we've got, since this is a perpendicular bisector, we know that AX and A prime X are the same distance. We know these are both right angles here. And of course, this line segment from B to X is congruent to itself. So by side angle side postulate, that's a triangle congruence postulate, these two triangles are congruent to each other. That is, BAX is congruent to BA prime X. Corresponding parts are congruent, so AB is congruent to line segment AB is congruent to line segment A prime B prime. So distance AB is equal to distance A prime B. Of course, B and B prime are the same. So we have AB equals A prime B prime. It preserves distance in that case. Okay, case 3, suppose AB is parallel to M. So that means that the line containing AB, the line containing A prime, B prime, and M are all three parallel to each other in pairs there. In this case, we've got these line segments going from A to A prime and B to B prime. Since they're both perpendicular to line M, they're also perpendicular to these others. Okay, so that makes this a rectangle here, and makes it a parallelogram, but it's actually better than that. It's a rectangle. Okay, and so opposite sides of parallelograms are congruent. So A, B, and A prime, B prime are the same length. Again, it preserves measurement. It matches or maps a line segment to a congruent line segment, one of equal distance. So in the other cases where these are not parallel, we're going to let the two lines need to intersect. Okay, and they're going to intersect the mirror line at a point W. And W is not going to be the same as B or A. Okay, so that's case 4. And this is going to be where A and B are on the same side of the mirror line. So it's going to look something like this. Now in this case I have B between A and W. It could be A's between B and W, but it doesn't really matter. Just relabel if they're not. Let me pull that down here. Okay. All right. So notice what do we have here? Let's see. So if X is the let's see, make sure I said that. So let X be the intersection of A prime with M. There it is. And let Y be the intersection here. So Y is going to be the midpoint of B prime, that segment. And the line segment from A to A prime is also going to be perpendicularly bisected by M. So that's X is the midpoint there. So we have AX and A prime X are the same distance. BY and B prime Y are also the same distance. Okay? And of course, the distance from X to Y is the same. Okay, so now what do we have here? Let's see. Well, we have a quadrilateral with, okay, look at these two quadrilaterals right here, ABYX. Well, let's see, I'll set it this way, AXYB, and that should be A prime XYB prime. They have both right angles here. They have line segment here and here congruent, one here and there congruent. So you've got side, angle, side, angle, side. We proved earlier that that's enough to make the two quadrilaterals congruent. And so among other things, that makes these line segments AB and A prime B prime congruent to each other in the same length. So therefore, once again, AB and A prime B prime are the same length. So if you want to prove that these two quads are congruent, look at a diagonal. Use some of your triangle congruence theorems a couple of times there and see if you can figure out how to write a proof of that. Okay, another case. Suppose the line AB intersects M at a point W, and A and B are on opposite sides of M. So it's they're on opposite sides of the mirror line, like this. That's another possibility. Well, in this case, W is here between A and B, and then our mirror image is here for B prime is over here, and A prime. So A prime is on the same side of the M as B. B prime is on the same side of the mirror line as A. So we have this set up. Once again, we'll let X be the midpoint here of this line segment A prime, where it intersects this line M, and Y is going to be the halfway between B prime and B here, the midpoint there. And again, that's where it intersects this line here because of a definition of what a reflection is. Okay, so what else do we have? Well, we've got some congruent triangles here again. So we've got side angle side makes triangle B prime YW congruent to triangle BYW. So this B prime W is the same distance as BW. And similarly down here, we've got an isosceles triangle here as well because um, this line segment AX and the line segment A prime X are congruent. We got right angles there that are congruent. And this line segment here is congruent to itself. So the two triangles here, AXW and A prime XW, are congruent. Now, since W is between A and B, then AW plus WB is the distance from A to B. Okay. So we see that reflections preserve distance and they're thus isometries by definition. On earlier exercise, we proved that isometries map a preimage to a congruent image. So once we get this as an isometry, we get that it is a congruence mapping. Okay, so what were we able to do here? Okay, we were able to prove this proposition. What was the proposition? That a reflection is an isometry and thus a congruence mapping. Okay, so it maps congruent lines, a line segment to congruent line segment. It's conformal since as well. It maps an angle to congruent angle, a triangle to congruent triangle. Okay, and notice a big piece of that was the side angle side congruence postulate. Okay, all right. And so using the SAS postulate from it and the other postulates, we're able to eventually prove the reflection theorem as a proposition. Now, if you remember, in taxicab geometry, it satisfies the other axioms of Euclidean geometry, but violates the SAS postulate. We know the SAS postulate is independent of the other postulates, and it must be taken as a postulate, not a theorem. Or we need to take something else as a postulate that would imply the SAS postulate as a theorem. So an alternative way of doing things is instead of accepting the SAS, or what we call a postulate, as a postulate, we could accept instead a reflection postulate that says a reflection maps a preimage set to congruent image set. So then with that as a given, then we can prove the SAS postulate not as a postulate now, but as a theorem. So here, for this one time only, we're going to assume that the reflection statement here is actually a postulate, and then we're going to prove that what would normally be the SAS postulate is now going to be the SAS congruence theorem. So we're going to need to show there exists a series of reflections that can be composed to finally produce an isometry which maps the first triangle to the second if we're given the hypothesis of the SAS postulate. And this is the idea behind the following GeoGebra activity. So there's the link to it. Okay. So what we're trying to prove is as a theorem, assuming the reflection postulate, we're given triangle ABC and a triangle A prime, B prime, C prime such that AB is equal to A prime, B prime. The measure of angle ABC is equal to the measure of angle A prime, B prime, C prime, and that the distance BC is equal to B prime, C prime, or you could state these in terms of congruent line segments instead. So if the SAS condition is satisfied, then triangle ABC is congruent to triangle A prime, B prime, C prime. Now, the way we did it, remember, there was no way to prove it. It was a postulate, right? So this, instead of it being a postulate, we're going to think of the reflection postulate as the reflection statement here as a postulate. And we're going to prove the SAS theorem. So if we click on this here, that takes us to this here. So here, basically, if you kind of watch what's happening, you're showing that if we have a congruent line segment here, a congruent line segment and angle here, right? So we're going to make a triangle right here. We're going to prove it's congruent to this one, and you can see the transformation happening. Look, this is so what they did is they did a translation. What's this? So right here, we're translating so that this point down here is fixed. And then we're going to rotate, and that's going to end up getting this here. Now this one here, to get it over, it's also going to require a reflection to get this to be congruent. Okay, so you maybe had to reflect it first and then do that. Okay, so there was some combination of things that we could do there. Okay, so we're going to do something similar to that. This is not really a proof. It's an idea behind the proof. Okay, and now we have to actually write down the formal proof. Okay, so we assume that a reflection maps a triangle to a congruent triangle. That's going to be something we know is true. Okay, it's a postulate. So we're given triangle ABC and a triangle A prime B prime C prime, such that all the hypotheses is true that from A to prime to B prime is the same distance as from A to B, that the angle at B is congruent to the angle at B prime here, and that the distance from B to C and the distance from B prime to C prime are the same. So we know that a reflection maps a triangle to a congruent triangle. Then what we're going to do is we're going to find a series of reflections that when they're composed, they map A to A prime, B to B prime, and C to C prime. And since a reflection maps a triangle to a congruent triangle, then this composition will produce a congruent image at the end. In fact, each stage of it will be a congruent triangle. So we're going to do this one step at a time. Okay, let me start building this thing up in GeoGebra. Here we have a general triangle ABC. It's going to be best to see what's going on if we make sure this is, some kind of scalene triangle. Here we have a point A prime. Now I'm going to make sure this is congruent, so I'm going to use what we know earlier. I want to do a circle by center and radius, which is going to be the distance from A to B. So we know that B prime has to be on this somewhere. Okay. And then where does C have to be? So we want to circle by center and radius. We want to go from A, and the distance needs to be the distance from A to C. And then we need to go a circle centered at B, where the radius is the distance from B to C. And we need to be where those two circles intersect. So I'm going to make this a little bit smaller so I can see it. So now I want to find the intersection points of those two circles there, and that's what we have. I'm going to leave the circles, I think, just for the moment, but I'm going to try to hide them a little bit by going to the settings, making them let's see, very thin, dotted, and maybe even a lighter color or something. So now you probably can't hardly even see them, but they're there. They're still there. Maybe I made them too light. Okay, so there they are. Okay, so now let's make the triangles. So there's actually two possibilities here. There's here to here to here to this one, or here, or I could go over here to this one here. So this is either one of these could possibly be C prime. We'll name that one C prime. We'll, oops, let me cancel. Rename that one C prime. And we'll rename this one C. Oh, double prime will be fine. Okay. All right. So we have that set up, right? So we know that corresponding sides here are congruent. Those are congruent. We made sure that these were congruent. And then we also made sure that these were congruent. Okay. So by side theorem, which we can proved earlier, if we know the side angle side theorem, we can prove that. So we know that these are going to end up being congruent from our earlier work. So now the question is, how can I take this triangle, map it to this triangle here, just using reflections? Okay, so let me see if I can do a side by side here. Okay, I went ahead and just paused it and fixed up this uh, GeoGebra activity a little bit better. So here we are starting over here with a triangle here, a general triangle ABC. Using circles, we were able to construct a congruent triangle here. We know the circles thing works because of the side property, but let's not assume we know that right now. What we have is triangle there with all the corresponding sides are congruent, and we can measure the angles. The angles are all congruent as well. So what we want to do is somehow get from this triangle to this triangle, the original pre-image triangle ABC, to triangle A prime, B prime, C prime with a series of a sequence of reflections, okay? And it's going to turn out we can do this with 3 or fewer reflections. So here we go. First, we want to try to get A to A prime. So how can we do that? Well, if we want a reflection that goes from A to A prime, we first just take this and make the line segment here from A to A prime. Take the midpoint there, make a perpendicular line through that, so the perpendicular bisector. That's going to be our first mirror line. Now, reflect this triangle over that, the original triangle over that line, and notice that A will go to A prime by the definition of what a reflection does. B will go to B double prime, C will go to C double prime. See, it doesn't matter where I put this, we're going to get that reflection happening. And this can be, this point A can be anywhere we want, and B can be anywhere we want. Now, at this point, you might be done, maybe, in which case you don't do it anymore. But if not, so if B is the same as B prime, skip the next step. But if it's not the same, we need another step that sends if B prime is the same as B double prime, you can skip the next step. But if it's not, we want to make sure that B prime goes to B. B double prime gets mapped to B, so we need prime. So we want another step. So we do the same thing again, make a line segment going from B double prime to B prime, and do a perpendicular bisector there. Now it turns out this is an isosceles triangle right here. So we know that, we know that if we take a perpendicular bisector of that line, it will actually go through this A prime as well. So this is going to fix A prime. So once we got, this doesn't screw up what we worked on hard to get A to be A prime to be our image of A. Okay, so now we're going to flip over this line. That gives us this triangle. So that one's flipped over there. Again, doesn't matter what this looks like to begin with, right? We can get that flip wherever that is. Well, it could be over here maybe even. So it doesn't matter. All right, now at this point we might be done if C prime and C triple prime are the same. So notice that this second reflection is going to leave A prime alone. It's going to map B double prime to B prime. And C double prime is going to be mapped over here to something that's C triple prime. Now, if that's the same as C prime, we're done. If not, we just do one more step. And this time, we're going to do the perpendicular bisector there. Now, notice this time, this perpendicular bisector is going to go through A prime and B prime. Again, no matter where this was to begin with, or where this is. So, in fact, this image is going to be over here. And then finally, we reflect over here, this mirror line. So there's our third mirror line. Okay. And so it's going to leave A prime and B prime fixed, but it's going to send C double prime to C prime. And therefore, it's going to send that whole triangle. So this triangle we had to start with gets mapped to the one here by the first reflection. Reviewing real fast. First reflection there. Next reflection gets that one mapped over, and the third reflection is there. At any one of these stages now, if we have, at the first stage, if A and A prime are already the same, skip step 1 and 2, or I guess 2 and 3. Okay? If at this next, then at that point, if B and B prime, B double prime and B prime are the same, then skip the second reflection, and skip the third reflection if C triple prime and C prime are already the same. So you'll be able to get this done with 3 or perhaps fewer reflections, no matter what we started with. So it's a pretty cool setup there. Okay, so we've shown we can map this triangle to this triangle over here with the series of reflections. Now, what if we were just given that this side is congruent to this side, this angle is congruent to this one, and this side is congruent to that side, side angle side? How does this prove that these two triangles have to be congruent if we assume that reflections are congruence mapping? Well, that first reflection is going to map to a congruent figure. So, among other things, the side length here is congruent to this one. The angles are congruent, and the sides are congruent again, as are the other parts. Next, we map another second reflection. It's going to keep this side fixed from A to B, A prime to B prime, and then it's going to reflect over here. I'm sorry, let's go back. I'm sorry. It's going to leave point A fixed, but it's going to send B double prime to B prime. And among other things, that keeps this angle fixed, size congruent, and these sides fixed, size. 6 keeps them congruent. Now our final reflection, okay, is going to send this triangle here up to here. It leaves line segment A prime B prime fixed and maps here. Well, again, this is going to fix this a congruent triangle, and it's going to have all the vertices the same, and that is the original triangle that we were trying to map to. So that means that the green sides must have to be congruent. The angle at A prime and its angle at C prime have to be congruent to the angles at A and C here as well. Okay, so that proves that if we assume that we have a reflection postulate, this is going to prove that the SAS theorem, that condition, is enough to make the triangles congruent. Of course, I usually do it the other way, assume the side angle side postulate, and then prove that a reflection is maps a congruent triangle to a congruent triangle, which I did at the earlier in this same video. And there's the proof written out. So when you put these two things together, the fact that if we have a reflection, if we have the SAS postulate, which we do the way we do it in my class, then we can prove the reflection theorem. Reflection is isometry and thus maps pre-image set to a congruent image set. However, we could also accept the reflection statement as a postulate and then prove the side angle side congruence was for us the postulate, but now would be a theorem. So these two things are logically equivalent. You have to accept one of the two as a postulate, and you can prove the other one as a theorem. My class, I assume the SAS triangle congruence postulate, and then we prove the reflection postulate, but it's a totally legitimate approach to do it the other way around. Of course, once you have proved the SAS postulate as a theorem, no longer really a postulate, then you can proceed the rest of the course just like we did before, using it as a reason to help prove the other congruence postulates, congruence theorems. Or you could possibly have alternate proofs of some of them using reflections as well. Okay, but the rest of the course would continue on if you chose the reflection postulate instead of the SAS postulate. You just prove the SAS theorem, and then the rest of the course works just like we did had before.